Okay, now we've looked at line integrals for scalar functions. Now we're going to look at line integrals for vector fields. So we shift gears a little bit. And the way we think about these, we completely get away from this whole thing of area and thinking of, okay, this integral deals with area. Remember, integrals sum up a bunch of stuff. That's what they do. Now, what I want to do is just remind you of, just like we use area to motivate what an integral is. When we first introduce integrals, we use area. When we do scalar line integrals, we use area. We can't always do that, and that's not always how you, well, that will not always help you conceptualize what's going on. With vector field line integrals, what we use is work. We use this physics notion of work. And we think of a path going through a vector field, and we think about, well, how do you measure the work done by that vector field to move this, move a particle along a path or whatever. Now, I want to remind you about work, and I don't want to get too involved in it, but remember what you're going to have is you have a force, okay? And this force is acting on something. And maybe something is being pulled in this direction, okay? In this direction right here. Well, what we do, and there's some angle here, it doesn't matter, but you're pulling, a force is acting in this direction, and the motion is in that direction. Now, when we talk about work, what we're doing is we're saying, okay, what is the magnitude of the force in the direction of the displacement? Okay? So what we want to do is we want to take the magnitude of the force in the direction of the displacement. Okay? And then we multiply that by the magnitude of the displacement. That's what we're going to do. Okay? So the magnitude of the displacement here. Looks like I have a long arrow over that D. Okay? So let's do that. Let's take this force and let's project it down onto this displacement vector here, right? That's what I'm going to do. I'm going to take this thing and project it down here. Now, so here's what's going to happen. Now remember, if we project, we talk about projection. If I project that vector onto this vector, here's what happens. We're going to have the dot product over the magnitude of D squared times, D. So this is just kind of general here. Now, that's the projection. And this represents the force going in the direction of the displacement. Now, let me take the magnitude of that. And I'm going to be a little bit careless because I'm going to take the square root of something squared and just call it positive. And it would be here because notice that the force is acting in the direction of the displacement. So it's going to be positive. In other words, what I'm going to be able to do is I'm going to say the magnitude of the projection. This magnitude is going to be equal to this. This thing, the square root of this thing squared is just itself all over this thing, and then this is something that changes here. Okay? Okay? Now, look what happens. If you go along with this, what you're going to see is you're going to see that this is really F dot D over the magnitude of D. Because this D gets rid of that, right? Okay. Now this represents the magnitude of the force going in the direction of displacement. Well, if we want to know what work is, just take the magnitude of the force going in the direction of the displacement and multiply it by the magnitude of displacement, right? So let's do that. magnitude displacement. Oh, look at this. F dot D. Okay. Work. Yeah. Well, that's right. We got rid of the square earlier. Okay? Now, let's bring this up to talk about a vector field. Okay? So, let's suppose that we've got a curve here. Okay? And let me just look at the direction of this curve at this point. Okay? I'm looking at the direction of this curve. Now, and this doesn't look exactly right. Let me see if I can make it a little more palatable. Okay. Now, that is the vector that's tangent. It's going in the direction of this curve. And let's suppose that this curve is, well, R. Let me just do this. This is the curve, right? This is the path. And this right here, what would this vector right here be if it's tangent? Yeah, this would be R prime, right? In other words, R prime is representing the direction that this curve is going. It's like the direction of the displacement, right? Now, we've got a vector field, and there's a vector field associated with that point. Maybe the vector is there. Now, that looks a lot like the picture I just drew a minute ago, right? So we might say, I think what I want to do is calculate work. Well, we just found out that work is going to be F dot R prime, right? Okay. That's what we just figured out. Now, I'm taking a little bit different approach than I do in your text because they use the unit tangent vector and get to where I'm going here. But can everybody see that this is reasonable? Because we just projected that force down on the direction, and there's what we got. Now, let's think about this R prime a minute. Let's think about, so we've got R of t, and so let's see what this is. R prime of t is, well, let's see what this is going to be. This is going to be actually, let me make this. Let me do this a little bit differently. Okay, so let's suppose we've got our vector and we want to do dr dt. Okay, dr dt. Now dr dt is going to be, well, it's going to be x prime of t, y prime of t, right? Does everybody see that? That makes sense, right? Okay. Now, I mean, that's R prime. Now, let me do this. I'm going to do the same thing I did when we were talking about, when we were developing the thing with line integrals and scalar functions. Let me just write this in differential form. You can kind of think of it as I'm multiplying by dt if you want to. But if I do this, I get dr is equal to this thing. X prime t, y prime t, dt. Okay. So in other words, it looks like what I'm saying is I'm going to think about, now remember, we're adding up. I calculated, I was a little bit careless, but you can see I calculated work here. And imagine if we do that all up and down this curve, all down this curve, this path. And I add those up. Well, what we would be adding up would be this. we have a curve, and we're going to take the vector field dot dr. And this is how we're going to, this is a line integral represented by, with a, for a vector field. Okay? Now, here's the thing about, one of the big differences is when we talked about a scalar line integral, the direction did not matter. If we start at A and go to B or B and go to A, the direction does not matter. That's not the case with the vector field. Because, remember how we're defining this. We're defining it with work. We were defining that other one, we were thinking about area. And the area doesn't change. If you look at the area of this fence, we were talking about which way you go. But here it matters because, I guess the easiest way to think of it is, think of gravity and the work done by gravity. The work done by gravity, isn't it positive? Unless I pick up something. So if I've got a chair, the work done by gravity is positive. What if I pick that chair up? Well, then it's negative. So you can have negative work, right? So if I drop the chair, okay, positive. If I pick it up, then it's negative. So you can have negative work. So you can have negative vector value. This can turn out to be negative, right? Depending on the path. If you go the opposite path, you're going to get the opposite value. Okay? Any questions about that? So this is what we want to keep in mind, this right here and how to interpret that. So let's look at some examples. Okay, here's a nice example to start off with. So we've got two vectors now, which we're going to dot product. Remember earlier we didn't have vectors at all when we were doing scalar line integrals. So I want to do this one. So here's the way we start off. I've got a vector field and I've got a path. And, I was even told the interval here. So everything is set out for me. So here's what we want to do. In place of the f, I'm going to put in the parametricized values, or the expressions. Okay, so we've got, instead of y squared, I'm going to have negative sine squared. Okay? Because y equals sine t. So in place of y up here, I put sine t, comma. Now, then I have cosine t, sine t. And I'm going to dot that with the derivative, right? dr. Okay? The derivative is going to be negative sine t, cosine t, dt. Now we have an integral that we can deal with. And we're going from 0 to pi. Any questions about that? Now, our job now is just exactly the same as it was in Calculus 1. This is just a basic Calculus 1 integral. So let's see what we've got now. We've got 0 to pi. If I dot product this, I'm going to get sine cubed t, and it's positive, and then I get cosine squared t sine t dt. My goodness, what a difficult integral, huh? You think it's difficult? Maybe it's not as difficult as we think. If I factor out a sine, right? This looks like maybe it's a difficult integral until you realize, hey, I enjoy factoring, so I'm just going to factor for the fun of it. So I'm going to factor out a sine t. And then I get sine squared t plus cosine squared t. I just love the Pythagorean identities, right? Because that's 1. And now we have an integral that a 2-year-old could do, right? It's just sine t dt from 0 to pi. Okay. And the antiderivative, so this would be negative cosine t from 0 to pi. I'm going to go ahead and work this one out because, we have to be careful of these signs, the negative here. Okay, so I put in the pi, and I get negative cosine of pi minus negative cosine of 0. Let's see what I get here. This is going to be negative 1 plus 1. I think that's going to be a 2. Okay. So it turned out nicely. Okay, any questions about that? So this is a line integral with a vector field. So it's a little bit different perspective. Okay? A little bit different way of thinking about it. Any questions? Okay. Now, I want to look at another one. Here's another vector field line integral. Now, what I want to do is I want to pause a moment and let y'all try this one. And then I'm going to show you some alternative notation that we could use. So let me just pause a moment. Okay, so first thing we need to do is figure out a way to parameterize this curve. In order, the direction matters. We got to go from 4, 0. And I'll try to think out loud here, and maybe so you can see the thought process. I go from 1, 3. Now, the easiest thing, I think, is to just say, okay, at the very beginning, I want x to be 4 and y to be 0, but I'm thinking about the x. So I'm just going to say 4 minus t. Now, once I get that, I'm kind of locked in because now, what I'm going to do is I'm going to say I want t to start at 0. Okay, that's going to give me a 4, but I want it to end up at 1. Well, if that happens, I just have to go to 3, right? Okay, now, since that's the case, I can look over here and I can say, okay, I want y to start off at 0. So I'm going to need to say, well, that's going to be like 4t. And we'll just see how this works. You can play around with this, and maybe I'll do minus t squared. I mean, you want it to have a square in it somewhere, so it would be parabolic. But if you look at this, if you put in a 3 here, you get 12 minus 9, which is a 3. So this thing does go. If you put in a 0, you get 4, 0. And you knew you had to get a 0 here because it was 0. So I just attached a t to everything. And that's a way to get a 0. And then up here, I needed to get a 3, so I just kind of played around with it. 4 times 3 is 12 minus 9. Yeah, that works. Okay. Okay, so I think that might be the hard part. Okay, so now what do we have to do? I need to get the derivative of that. And I get negative 1, 4 minus 2t. Okay, there's what we've got. Now I've got to dot product that with the function. So here we go, y x squared. So now, okay, so I'll do this. And by the way, I'm going from 0 to 3 here, 0 to 3. Now in place of y, I'm going to put 4 minus 2t. Is that right? Is that how this thing worked? It was y and then x squared. Okay. Oops. So what is x? Actually, it's not 4 minus 2t, is it? 4 minus t. Okay. And then you look up here and you say, well, what was my y? 4t minus t squared. And that's what I put in. Well, for the y, I put 4t minus t squared, don't I? Okay, that's right, because the first thing was y, wasn't it? It was y comma x squared. Now, what is x? 4 minus t? Okay, I think that's got it, right? So remember, it was y x squared. Let's just make sure we got it. This is y, 4t minus t squared, and then the x. Okay, I think that's good. I think we got it. Now I'm going to dot product that with this thing. Put a dt there. Actually, let me not put the dt there. Let me just come down here. Okay, so we're going to have negative 1, 4 minus 2t dt. Okay, now there's what we have to integrate. Okay. Now this looks like it's going to be manageable, right? Because we don't have any radicals or anything like that. But let's go ahead and just work through it and see what we come up with. Okay, so we've got 0 to 3. If I dot product, I'm going to have negative 4 plus t squared. That's when I multiply this times negative 1. Just changes all the negative 4t plus t squared, right? There we go. And then I've got plus 4 minus t squared times 4 minus 2t. Now let me know if I make any mistakes here. Multiplied the x's together. They just changed their signs. And then I multiplied this one. Okay, good. All looks good. Okay. Now let's see what we can do with this. I don't know, what's the best way to integrate this, you think? Just multiply everything out? Maybe that's the best way. I guess so. I guess I'll just multiply everything out here. Okay, so I've got negative 4t plus t squared, and then plus 16 minus 8t plus t squared. Let me factor a 2 out of that. Put it right there. And then this is just going to be 2 minus t. Okay, there we go. Well, I factored a 2 out of there and just put it in the front, right? Okay. I mean, it wasn't really necessary. I just didn't want to keep having to multiply. I mean, I want to make my numbers smaller. Okay, now let's see what this is going to be. 0 to 3. And now at this point, it's just, just hoping we don't make a mistake here. So here I go. If I multiply this out, here's what I get. I get 2 times 16 times 2, that's 32, minus 16t. And then another minus 16t, right? And then plus 8t squared. Okay, right? Now, let me know if I make a mistake here. 32, negative 16t, negative 16t, 8t squared. Okay, now we're at the t squared. So this is going to be plus 2t squared minus t cubed. All of this dt. Okay. Now, as we go through this, in a minute I'll probably just stop, and because I know you can integrate at that point. You can see that we would continue on adding this up, and I think that this thing turns out to be like 69 thirds is what I think it turns out to be. But for this, I think I won't continue on with that because I worked this one in advance and I get stuck and waste time. It's actually 69 halves, so okay, 69 halves. Okay, well, that's what that integral turns out to be. I mean, if we work through all that process, it should be 69 halves, unless I made some mistake there. Okay, any questions about that? So that's how we can integrate. That's how we can deal with these line integrals for vector fields. Now, let me just point out something here. Sometimes, if you think about this, if you think about this, this thing, let's suppose that we've got, something over here in the x and something over here in the y. Okay. And if I differentiate here, okay, so if I do dr dt, and this is dx dt, dy dt, okay? You think about that. So we're looking at an alternative notation that you'll see sometimes. That kind of makes sense, right? Now, if I do this thing once again where I'm kind of thinking, oh, I'm multiplying through by dt, if I think about that, but I'm writing it in differential form, what we get is dr is equal to dx dy. Okay? Okay, that kind of makes sense. Okay, the derivative of x, the derivative of y. So let's see where that brings us. So we've got this vector field. And it's mn. Now I've just been doing 2 dimensions, but you can do 3. Okay, and then I want to say, okay, I'm going to dot product that. But dr is equal to this, right? So I'm trying to help you see where this alternative notation, what kind of motivate how you can use it. Now this is going to look kind of funky because you've not seen an integral written this way before, but is everyone with me on this? Now let me dot product it and let's see what we get. We get m dx plus n dy. There. Now we can do this with vector fields, okay? Does everybody see that? Now I want to take the vector field that I just worked, and we know the answer comes out to be 69 halves. For time's sake, we didn't go through all of it. But this is the alternative way we could look at that. And I want to go back up. Let's remind ourselves what that function was. It was yx squared. Okay? So let's look at that. Okay? So here's what we have. We have yx squared. And let's dot product that with dx dy. And we're going to come up with another integral here. Okay? So if we do that, we're going to get y dx plus x squared dy. Okay? That's this, right? Okay? Now, this function, now remember, we were integrating, this particular function was 4x minus x squared. Okay? 4x minus x squared. Okay? So we know what y is. Y, no, hang on. Y is 4x minus x squared. Okay? Let's find out what dy is. dy is 4 minus 2x. Okay? Everybody see that? Nobody can argue with that, I don't think, right? Well, let's not do that. Let's just bear with me here, because we are being sloppy. Okay? We are being kind of sloppy. Well, yeah, okay, yeah, I see what you're saying. Yeah, let me go ahead and put a dx. That's right. We'll put a dx. Okay, now look, here's what we've got then. In place of the y, I'm going to put 4x minus x squared dx. Okay, so notice, in place of this y, I did that. And then I've got x squared, and in place of dy, I will put 4 minus 2x. There's what we have. Okay. Now we're back to kind of the integral that even a baby could integrate, right? It's just a straightforward, I've got dx here, dx there. Now, here's where you have to be careful, because we're not going from 1 to 4, right? We're going from 4 to 1, right? X is 4, and we're going to 1. So I've got to go 4 to 1 like this. Remember, the direction matters with these vector fields. So there's what we have. And now let's see if we can integrate this. This is 4 to 1. Now this one right here is going to be 2x squared minus 1/3 x cubed. Okay, and then we've got plus, this is 4x squared, so that's going to be, is that going to be 2x squared? Well, 4/3 x cubed, right? If I distribute through there. And then this is negative 2x cubed, so that's going to be, is that going to be negative 1/2 x cubed, x to the 4th? Oh, I already integrated, didn't I? Oh, I don't need this integral. Now, did I get all that right? Because this is 4x squared minus 2x cubed. So this is 4 over 3, yeah? And then this is negative, yeah, I think that's right. Any questions about that? 2x squared, okay. Now, I'm going to put in the 1. And, of course, I get 2 minus 1/3. Actually, before I do this, let me simplify this a little bit. And I think the simplifying is going to save us a little time. But how many x squareds? I've got 2x squared. I've got negative 1/3 and 4/3. That's 3/3, right? 3/3 is 1. So this is just an x cubed. And then I've got minus 1/2 x to the 4th. Okay, so that might save us a little bit of, just a little bit of time. I don't know. Now, if I put in the 1, I get 2 plus 1 minus 1/2 minus, okay, if I put in the 4, I'm going to get 32 plus, well, let's see here. Is that 64? Minus, now what is 4 to the 4th? Actually, is it 256? So this is 1/2 of 256. Is that right? Did I get all that right? Okay. Now let's see, what does that turn out to be? If we work through all that, what we get over here is we get 3 minus 1/2. Well, let's see here. That's 2.5, right? Is that 5/2? Okay. So we've got 5/2 here, right? Now let's see what this is going to be. Minus 32 and 64. That's going to be 96. Is that right? 96 minus, what's half of 256? Huh? 128. Okay, so what is 96 minus 28? Huh? What is it? Negative 32. Is that right? Okay, so that's going to be a positive 32, right? Okay, so we get 5/2 plus 32. 69/2. Okay, so that's 69/2, right? Okay. Now, so you can see we got the same answer, right? Now, we didn't work completely through the other one because it was just too much time. But any questions about that?